Archival black and white footage of 1990 Desert Shield ship, convoys crawling across the Atlantic. Slow-loading sea, 5 galaxies on dusty Saudi runways, overlaid with modern high-speed sea, 17 landings at Al Udeid Air Base. Dramatic but understated music fades quickly. Cut to split screen, old versus new timelines. In 1990, it took the United States 5 months to build up forces for Operation Desert Shield. In early 2026, America surged thousands more troops into the Middle East in just weeks. Viral headlines scream 30,000 U.S. Rangers and elite Delta Force troops arrive. The physics and engineering reality is more interesting and far more impressive than the hype. Today, we're dissecting the civil infrastructure and logistics backbone that makes this kind of rapid power projection possible. Not the guns or the operators. The runways, the warehouses, the fuel farms, and the unforgiving laws of stress, strain, and energy that still rule every deployment. Animated map of CENTCOM region showing current 50,000 total U.S. troops. Pre-surge baseline 40K. Highlight recent additions 3,000-4,000 from 82nd Airborne. 2, 500-plus Marines from USS Boxer/Tripoli, 100 of SLF, Rangers, Delta Elements, SEALs. Red circles on prepositioned stock sites in Kuwait, Qatar, Jordan. The driver is simple: geopolitical pressure. Tensions with Iran have prompted the Pentagon to increase options for the president. But moving even a few thousand troops and their equipment 7,000 miles is never just about boarding planes. One soldier in sustained combat can require 20 to 30 pounds of supplies per day: food, water, ammunition, fuel. Scale that to thousands of troops, and you're talking hundreds of tons daily. That's the economic and military driver. The constraint? Pure civil engineering and logistics physics. Visual: simple animation of the logistics multiplier. One tank icon requires 5 to 10 support icons: fuel trucks, ammo maintenance. Graph: fuel burn to carry fuel over distance. Cut to live action heavy C-17 landing, then slow motion tire deformation on tarmac. Show Westergaard stress formula graphic. Simplified sigma equals stress under wheel load. Here's the first principles barrier engineers have fought for decades. Load-bearing capacity meets the tyranny of distance. A fully loaded C-17 Globemaster 3 weighs roughly 265 tons at takeoff. When it lands in the desert, its 12 main landing gear tires concentrate enormous pressure on the pavement. Exceed the runway's design strength, and you get rutting, cracking, or outright failure. The physics is brutal and non-negotiable. Concrete and asphalt behave according to stress-strain relationships. Hooke's law and elastic range. But military runways push into plastic deformation territory under repeated heavy cycles. The classic Westergaard equation for rigid pavements tells us thickness must increase with the square root of the load and the modulus of subgrade reaction. In plain English, heavier planes demand dramatically thicker slabs, often 18 to 24 inches of high-strength Portland cement concrete over stabilized base layers. Desert conditions make it worse. Daytime temperatures above 50 degrees Celsius 122 degrees Fahrenheit cause thermal expansion cracks. Blowing sand acts as an abrasive, eroding surfaces. And every extra pound of fuel or ammo you fly in requires yet more fuel to carry it. The same vicious cycle that limits aircraft range. For 50,000 troops total in theater, you're not just parking planes. You need ports that can offload roll-on/roll-off ships carrying hundreds of armored vehicles, fuel farms holding millions of gallons, and supply depots engineered to survive months of storage in 120 degrees Fahrenheit heat without degrading explosives or electronics. That's why, for 50 years, the U.S. has invested in Army Prepositioned Stocks, APS-5, massive forward warehouses in Kuwait, Qatar, and elsewhere. The engineering challenge: store M1 Abrams tanks, Bradley fighting vehicles, and millions of rounds in a corrosive desert environment while keeping them ready to roll within hours of troops arriving. 3D exploded view of a modern military airfield. Runway cross-section showing 24-inch concrete plus base layers. Cut to time-lapse of C-17 unloading vehicles at Al Udeid or Ali Al Salem. Animated map showing APS sites lighting up. Interior climate-controlled APS warehouse with vehicles under dust covers. In-flight refueling animation. Graph. Deployment timeline 1991 versus 2026. Engineers solve this through layered, redundant infrastructure. Not one magic technology. Are the real hero. Instead of flying every tank from the U.S., the heavy equipment is already there. Troops arrive relatively light on commercial or military airliners. Then marry up with gear. One C-17 can deliver 100 paratroopers or platoons worth of light vehicles. Multiply by dozens of sorties per day, and use surge combat power in days, not months. Runways themselves are civil engineering masterpieces. Modern expeditionary airfields use AM2 matting or upgraded permanent concrete, designed for 1,000 plus passes of C-17s at maximum weight. The subgrade is stabilized with geosynthetics and chemical binders to handle the desert's shifting sands. Maritime prepositioning adds another layer. Squadrons of roll-on/roll-off ships loaded with brigade sets, anchored or docked within striking distance. Combine that with in-flight refueling tankers, and you break the range-payload trade-off that has haunted airlift since the 1950s. The 160th SOAR and Special Operations Aviation elements, for the smaller Ranger/Delta contingents, use forward operating locations with shorter, tougher runways engineered specifically for MH-6 Little Birds and MH-60 Blackhawks. Different load profiles, different pavement recipes. Side-by-side comparison chart. 1991 Desert Storm build-up 5+ months versus 2026 surge weeks. Real footage of troops offloading, vehicles driving off C-17 ramps. Result? What took half a year in 1990 now happens in weeks because the civil infrastructure was already engineered and paid for decades ago. Cost graphs, billions spent on APS and basing. Desert heat, damage time-lapse on equipment. Animated vulnerability map, showing missile ranges from Iran. Fuel consumption pie chart. Political map of host nation bases. But real engineering is compromise. Maintaining APS-5 and upgraded bases costs billions annually. Every surge burns through fuel at rates that would make commercial airlines blush. Desert sand infiltrates everything. Heat degrades rubber seals and electronics. Runways degrade faster under repeated heavy loads than the design models predict. Host nations have finite real estate. Expanding Al Udeid or building new facilities risks local backlash and diplomatic friction. You can't just pave over the desert without environmental and sovereignty consequences. Concentrated fuel farms and ammunition depots make tempting targets in a high-threat environment. Physics doesn't care about politics. A single well-placed strike can create cascading logistical failures. And the numbers? The 30,000 Rangers in Delta Force claim is marketing exaggeration. The 75th Ranger Regiment's entire active force is roughly 3,500 soldiers. Delta Force is even smaller. The actual recent surge involves hundreds of special operators plus several thousand conventional troops from the 82nd Airborne Marines, bringing the total U.S. presence to roughly 50,000. Still significant. Still an engineering triumph. But not the comic book army, the headlines suggest. Final infographic. Cost per soldier deployed, $1M plus initial surge. Timeline of future viability. Closing shot. Wide aerial of a massive desert air base at dusk with C-17s taxiing. Is this infrastructure viable long-term? Absolutely, for short, sharp surges. The prepositioning model has proven itself repeatedly. But sustained high-intensity conflict would still strain the system because the physics of distance and consumption hasn't changed. Economically, it's expensive. The U.S. spends tens of billions yearly on this global logistics network, yet it delivers something no other nation can match: the ability to project credible combat power anywhere on Earth within days. Slow pullback on the airfield to a globe view, highlighting U.S. bases worldwide. Fade to black with channel logo. Nature sets the limits. Stress, strain, energy, distance. Human ingenuity doesn't break those laws. It builds the infrastructure that works around them. The next time you see a headline about elite forces arriving in the Middle East, remember, The real stories written in concrete, steel, and carefully engineered supply chains, decades in the making and still bound by the same physics that has governed every army since the dawn of war. Subscribe, next video tease.